Hi, this is Mr. Anderson, and today I'm going to talk about radioactive decay, or radiation for that matter. What is radiation? Radiation is essentially parts of atoms that are given off, or energy that's given off by radioactive atoms. And so we measure that using a Geiger counter. This is a Geiger counter right here. And Geiger counter, inside this wand, you have some inert gases that every time they get hit by a piece of radiation, they give off a little bit of electrical charge, which you can pick up in here. And so a regular Geiger counter, when you turn it on, you're going to hear a little bit of static. And the reason why is that there's always background radiation everywhere. But if we put something radioactive in front of it, so let's say we put a big chunk of uranium-238 here, it's going to give off a huge amount of radiation, and you're going to be able to pick that up in here. And so this Geiger counter is just going to steadily increase. We can use that to do a lot of important things, like, for example, date how old the Earth is. And so there's a lot of stuff that comes out of that. So how does radiation work? Well, to understand radiation, you have to understand the fundamental forces that we have. And so if this up here is a nucleus, so the red ones are going to be the protons and blue ones are going to be the neutrons. What we find is if we look low on the periodic table, so this is neon, neon's going to have 10 protons and 10 neutrons. But as we move up the periodic table, so here we got the same number of protons and the same number of neutrons for calcium. When we move up to tin, you'll find that the number of protons is going to decrease compared to the number of neutrons that we have. And if we get up to uranium, we have 92 protons but 146 neutrons. Well, why is that? Well, the reason why is that the nucleus is held together using something called the strong nuclear force. And so all these nucleons are held together by this force which holds the nucleus together. Now the nucleus would love to shoot apart, and the reason it would love to shoot apart is you have all these positive charges up here, all these positive protons, and when you have a small enough atom, the strong nuclear force is able to hold it together. But when you get something like uranium, it's got 92 protons in the center, and so you have to have tons of neutrons to hold it together. And even with those tons of neutrons that you have, sometimes it has a tendency to fall apart. And so this chart takes a second to get your head around it, but essentially what we have on the bottom is the number of protons, and then on the side we have the number of neutrons. And so you would think if the number of protons and neutrons are always equal, then we have this perfect line that goes up here. But as I showed you on the last slide, we tend to get more neutrons the farther we go up. And so you can see that this graph tends to drift towards the neutrons. So as you get up way up here with like 82 protons, the perfect number of neutrons to have would be 126. And so what you find is that if an atom exists on either side of this perfect line right here, it's going to give off protons, neutrons, so sometimes they're going to change just to get back to that equal point, or that perfect ratio of neutrons to protons. And so this chart is neat in that it shows you what kind of decay we have. So if you're on this side of this line, you undergo what's called beta minus decay. If you're on this side, you're going to undergo what's called beta plus decay. And then as we get up towards here at the end, you're going to have a lot of what's called alpha decay. And then eventually we can have fission as we go far enough up. And so all of these types of radiation are ways for an atom to get back to that perfect ratio of neutrons to protons. Okay, so I've talked about why we have radiation, but what is this radiation? Radiation works like this. You can imagine the first experiments where if we take a radioactive material and then we allow it to shoot its way through like this, and then we have a sensor over here. If you have something radioactive here and then a tunnel right here, what you'll get is a spot showing up, or radiation showing up on this side. So what scientists wanted to do was they wanted to figure out what's the nature of this radiation. So what they did is they put a positive charge up here and a negative charge down here. If I remember right, they actually had negative on one side, but it doesn't matter. So what they found is that you had one spot showing up down here. So there was some particle that was going out that didn't have a charge. We had some that was actually being drawn in this direction, and then we had some that was being drawn in the other direction. And so we called these things alpha decay. Alpha decay has a positive charge, and so it would be drawn towards the negative. So we're going to have alpha decay down here, right? Alpha decay like that. We're going to have beta decay up here. Beta decay had a negative charge, so it's drawn towards the positive. And then we had this gamma radiation here that didn't have any kind of a charge. And so what are these types of radiation? First of all, if we look at alpha decay Alpha decay is simply 2 protons and 2 neutrons that are given off. And so without electrons, what is this? It's essentially helium. Helium has 2 protons. It has a mass number of 4, and so that's alpha decay. Alpha decay can't even move through a piece of paper, and so it's weak as far as that's gone. Next type is called beta decay. Beta decay is an electron, essentially. Electron has a -1 charge, and it has no mass. And so that's beta decay. There's another type of beta decay, and it's weird to write an electron here, but it has a positive charge. It also has 0 mass, and so we refer to that as a positive electron, or we call that a positron. But beta decay would be stopped by a little sheet of aluminum foil. And then the last type of decay, the one that doesn't have a positive or a negative charge, is called gamma radiation. Gamma radiation occurs when we have, remember, these strong nuclear forces that are holding this nucleus together. And as they start to wiggle and these atoms or the nucleons wiggle underneath their force, that energy is given off in the form of gamma radiation. It's not actually made of nucleons, neutrons, or protons, but it has a huge amount of energy. It's like X-rays, and it can only be stopped if we move it through large amounts of soil or lead as a way to stop it. And so those are the types of radiation, at least the types of radiation that you should understand. And so you also have to write nuclear formulas. And so when we did chemical reactions and chemical formulas, remember we had to balance those equations, and you have to do the same thing here. And so let's start with the one that I talked about at the beginning. So let's start with uranium-238. Now uranium-238 is undergoing, in other words, it's going to lose, let's go back for just a second, it's going to lose 2 protons and 2 neutrons. And so what it's losing is actually a helium nucleus, and so that has a charge of 2 protons, and it has a mass number of 4, since there are 2 protons and 2 neutrons. And so if you think about it, what does this become? Well, I'm actually going to start with my atomic number and my mass number up here. If you lose 2 protons, you're going to have a mass, or an atomic mass now, of 90. And if you lose a mass of 4, this is going to become 234. Now what's interesting in the nuclear reaction is we've actually changed the number of protons. Since you lost 2 protons, it's not uranium anymore. And so if I look up here, here's uranium on my periodic table. But if I lose 2 protons from that, it's not uranium anymore, it's going to be thorium. And so this is how you write a nuclear equation. You have to make sure that these all balance. The mass numbers balance and the atomic numbers balance as well. So what happens to uranium-238? It actually becomes thorium-234 over time as it loses these protons. Okay, let's try another one of those. And so let's say this time we're dealing with beta decay. So let's say we lose an electron. Electron, remember, has a -1 charge, and it doesn't have a mass number. And so what's something that undergoes beta minus decay would be cesium-137. So cesium-137 has a mass number of 137 and an atomic number of 55. And so what happens when it undergoes beta minus decay? Well, let's not write the symbol, remember, because that symbol may change. If we've got 55 protons and we lose 1 electron, what we actually gain is a proton. So this becomes 56. Where did it come from? One of those neutrons became a proton and gave off this electron. And so this becomes 56. What is the mass number? Well, electrons don't have a mass, and so that's going to be a mass of 137, or it's a negligible mass. And so what does this become? Well, we'd have to find cesium on here. Cesium is 55. Okay, so here's cesium right here. Cesium is 55 on the periodic table, but since we're gaining 1 proton, that actually becomes barium. And so this is going to become barium-137 plus that electron, which has a -1 charge and no mass. And so this would be, we call this beta minus decay. Okay, let's do another type of decay. And this decay we'll do is beta plus decay. So what do you lose in beta plus decay? You're losing an electron, but this is a positron, so it actually has a +1 charge, it has a mass of nothing. What's something that undergoes beta plus decay would be sodium. Sodium has an atomic number of 11 and a mass number of 22. And so if we lose a positron, so if we lose one of these with a mass of this, what do we get? Well, we're going from 11 mass number, or atomic number of 11. We're losing one of this, so this now becomes 10. This is not changed at all, so that remains at 22. And so let's look on our periodic table. Well, here's sodium right here. It's number 11. But if we lose one proton, we now become neon. And so when you're doing these equations and writing out the formulas, make sure that you go all the way across the top. So we've lost one of these, all the way across the top here, and make sure that we balance those out. In other words, the atomic numbers and the mass numbers of the reactants and the products have to be exactly the same. So that's radioactive decay, and I hope that's helpful.